By the way, my name is SIGCHI, and I'm the session chair for this invited lecture. And it's my great pleasure to introduce both a mentor, a great friend of mine, and someone I deeply admire, Stu Card. I worked with Stu at Xerox PARC for about 13 years. And while he was there, I got to know him doing lots of amazing work on the theories relating to HCI. Stu had an illustrious career at PARC, starting with the characterization of the mouse using Fitts law, and then later leading to actually help with the commercialization of the mouse with the Xerox Altos and Star machines. Then later, he actually led this group, user interface research group, which I was a member of for many, many years, and it was one of the most productive research groups in HCI, ending up with lots of important work around information foraging, information sent, and then one thing that a lot of people don't know about is that Stu actually helped commercialize a lot of the technology at Xerox as well, resulting in 3 companies and also lots and lots of patents, some 50 patents and 90 publications. Stu is a member of the National Academy of Engineering and received the 2007 Franklin Bauer Award for Achievement in Science. He's also an ACM Fellow, a ACM SIGCHI Lifetime Achievement Award winner, and a IEEE Visualization Career Award, as well as a member of the Chi Academy. Stu actually received his bachelor's degree in physics from Oberlin College. And one of the things that if you ever had a chance to work with Stu, and everyone who have worked with Stu, a lot of people who are sitting up here know about this, about Stu, is that he loves the reductionist aspects of physics. And he's always saying that, HCI science and theory needs to be just as reductionist. And so his PhD degree is actually in psychology in CMU, and he worked with a lot of very well-known people there, including Alan Newell and Herb Simon. He's right now a consulting professor at Stanford after he retired from Xerox PARC, and I think Stu actually and I had a bet many, many years ago, which was when the first time the Lifetime Achievement Award was given out here at SIGCHI. I said they were going to ask you to give an invited lecture. And that actually didn't happen because we didn't know that what to do with this Lifetime Achievement Award thing. It was brand new at the time. And so I remember that. And that bet was actually for a case of beer, which Stu never delivered to me. And I said that he was going to be invited, and he wasn't. And so as technical program chair, I basically used my powers to make this happen. So I'm very happy to see that there's literally hundreds of people here in the room to hear Stu talk about interaction science. And I'm really looking forward to this talk. So Stu, take it away.
Well, now I know all of this is really so Ed can get this bed of beer. Last time I talked here, I said some things that Peter Paroli seemed to like and was egging me on to sort of develop more. And so I decided what to use this occasion for was to really see if I could get a little farther down that road. So I'm going to give you a sort of little essay on theory in HCI today. The great thing about giving a talk like this is you get around those mean referees. You get to say what you want instead of saying what will fit into the formula for chi. So I intend to exploit that every inch. Well, I've been thinking about theory in HCI for a while. When I started thinking about it, I looked like this. And my ideas look like this. And more recently, I look like this. And now my ideas look more like this. And so I'm going to try and explain that. But to start out, I thought I would start with an example, a contemporary example, from Apple Mission Control. Now, I'm a real Apple fan, and so I look forward to their application Mission Control. And the idea of it is that it can scale up so you can handle more windows, and you can also switch between tasks, or windows at least, very quickly. And they do this by giving you little miniatures of the different workspaces. They have it so if you tap 2 fingers at a time on the pad here, then you quickly go into this mode. I bet some of you didn't know that. If you tap your space bar, it will make one of the windows appear. And so it sort of seems like an interesting design. The problem is it doesn't really work very well. The system whips to unknown spaces when you start a new app. You're constantly searching all over visually to find where did that window go now. You can't keep the windows together in the task in the same space. And Austin agrees, so it must be true. So why doesn't this thing work? Well, so what follows is a little chalk talk on that. Once upon a time, we ran one app at a time on the computer. And to run another one, you had to sort of get rid of the first one or else remember everything about it. But then Windows came along. And the people sort of underappreciate what Windows does for you. What it does is it allows you to integrate arbitrary applications together in the service of some task. And you can even have these interact so you can have things go from one application to another. Now the problem is that there's too many windows. But these windows are really related to different tasks that you're trying to do at the same time. So if you think of it that way, and you look at sort of where what you access after what you access, the pattern that you realize is that people access a whole bunch of windows within a task, and then they'll shift over to another task, maybe do it a little while, and then shift back. But there's a lot more interaction within a task, in the windows within a task, than there is between tasks. And this means that the system exhibits what's called locality of reference. This plots a probability that you'll access a window 1, 2, 3, 4 window accesses away. And so when you realize that, then you realize, gee, this is a lot like working set theory in virtual memory operating systems. There's a reference clusters and locality of reference. And the significant thing about that is that if you stay in a virtual memory operating system, of course you have this virtual system and then this physical system supporting it. If your working set, that is to say all of the mob of things that you're accessing together fits within physical memory, it's as if the virtual memory was real. But if it's too big to fit in, then all of a sudden everything goes to hell and the response time goes up sharply. Well, that sort of explains why mission control design isn't successful. First of all, there's a bunch of things that induce window faults. So these little thumbnails are too small for you to actually see what you need to see and find a window on it. And then the windows overlap in the center. But mainly, the activity model's wrong. It's organized around applications and not around tasks. So I understand in Mountain Lion that they're going to bring back expose for the Windows overlap. but that's not actually going to fix it because it's the wrong activity model. So the conclusion is until they fix that, the design is unrepairable. Well, now let's take the next step. How could we fix it? Well, since we've identified this phenomena with virtual memory operating systems, there's a thing called a preloading policy, which means that if you, instead of faulting the windows out and in one by one, when you know that you're referencing another group, you bring them all in at once and retire all the old ones at once. And this is a lot faster. So you can invent a visual analog of this. It would look a lot like workspaces. And so here, if you just take these reference things and make them into task-based workspaces, then, in fact, it's likely to work much better. But then you have to face another problem, is sometimes you want a window in more than one task at the same time. Well, to solve that now, you're going to have to invent a new piece of technology. Austin invented one for us once called placements. And this splits what a window is into two parts, the location part and all of the other internal part. So you see this one window is in two workspaces, in two positions, and in two different sizes at the same time, or at least that's the illusion. And so my first conclusion is that theories can be useful. By just talking this through for 5 minutes, we figured out sort of what was wrong with it. We figured out what we can do about it. And there's another advantage that we get out of doing that, is that we brought forth a number of abstractions. Now, these abstractions allowed us to see the relationship between these windows and something completely different in another space, virtual memory operating systems. And that wasn't a very obvious association when we started, but when we got this to the level of abstractions, it seemed obvious, and then we could use results from the one area and transfer them together. We can also grow the discipline with these things by gradually connecting phenomena together and building up a set of concepts. But not all theories are as useful. I once had the experience of working on an NRC study where we were going to try and use models to design the next generation of helicopters. And after doing this for a while in writing that book, I came to some conclusions. First, it's hard to integrate the models. This sort of shows there's a bunch of visual models on the one side, and then there's a bunch of cognitive models. And it was hard to put the different models together because they required very different assumptions. And there was nobody who was working on combining cognitive and perceptual stuff together at the time. But that's a central thing that happens in all the tasks. And so I came to the conclusion, I used to think that if you just sprinkled a little more fertilizer and water on the different models, eventually they would sprout and grow. I came to the conclusion that some models will never be useful, no matter how long they're developed, because they're developed with trade-offs that don't respond to the task to which they're going to be put. They might be useful for some things, but you kind of can't use them. What you often need is predictive zero-parameter models. You need that because you want to fit them into other things, and you don't want to have all sorts of assumptions that can't be met. That's because the purpose of these models is insight, not really data fitting, at least when they're of use. So the models that I like for this purpose, well, you might call theories with a purpose. They're sort of blue-collar models. You can do stuff with them. You can explain something, predict something, generate something, just do something. They tend to be mechanistic. You can do this by exercising some lower level mechanism on a task analysis situation. Herb Simon used to say, always have a secret weapon, by which he meant some level of calculation you can do lower than what people realize that you're actually doing. Maybe you even keep it private. And Herb Simon used to, when I was a student, come to the departmental colloquia, and about 10 minutes before the end of the colloquium, just when the speaker had worked up the whole hour to some conclusion, denouement, he was about to present, Simon would raise his hand and predict the speaker's results. Now, as a graduate student, I found this really great sport. I loved this. And so what I wanted was I wanted to figure out how I could do everything that Simon could do plus stuff he couldn't. So that was the basis of the model human processor I did later. It was basically all of the he used these little constants and just made little calculations. Whereas, you know, what a psychologist knows is 1,000 experiments, and they would reason by analogy. So my third characteristic is that they're teachable. You can teach strangers to do this. And moreover, they tend to get approximately the same answer. And so things that sort of don't count so much in this is frameworks and philosophical stances, and because they're not sort of specific and practical. Gurus don't count because it needs to be teachable. If somebody can come in and solve your problem for you, but that's the person solving the question is whether that's the person solving the problem or whether it's a theory doing it. So these things can still be beautiful, like sunsets and poetry. They just won't sort of start your car. That's the way I think of it. As Newell used to say, science is method, all else is commentary. And you see this expression on his face. You can see the glee with which, I know that expression so well. This is the cheerful way in which he would tell you you were full of crap without actually giving you offense. But, you know, the theory in HCI is sort of a mixed status. It's sort of limited. And why is that? Well, there's various reasons. I'll sort of have 4 listed here. One is that the role of science and technology is unclear. This is what confused me for a long time. Another thing is that it's hard to do, but it's not impossible, and there's many good examples around, so I'm not so worried about that one. Right now, it's the case that we actually need theories of new things, and I'm going to say something about that in a moment. But really, I think it's hard to make them easy to use, and it's hard to sort of learn them, and it's hard to convince yourself that they would sort of pay off. They need to be sort of intercalated with the rest of knowledge in sort of a deeper way. So let me take on this first question first, because this is a thing that confused me for a long time. What's technology? Well, technology is a means to fulfill a purpose. This is Brian Arthur's definition. It's based on some principle of this thing, some essential idea that makes it work. So we had the window workspaces. Well, the purpose was to access many windows without incurring large overheads, and the window workspaces were what made it work. How the process doesn't work is sort of what the received wisdom was from Vannevar Bush, that there's basic science, you figure something out, and then there's applied science that sort of refines it, and then finally there's technology and products that you sell in the marketplace. That's what I started out thinking it works. But there's lots of puzzles, because technology can actually evolve quite well without science, thank you. So here's a bicycle, and even though, you know, on the 1885 model, you can see a slight bend of the fork forward. If you bend the fork backwards, it's unrideable. So that's subtle, but there wasn't really any science done that influenced the development of the bicycle. There's science after the fact. or even the steam engine where you'd think there would be. There's only science that sort of came in a couple little places. The rest was more or less done by tinkering and trying stuff. So there's 3 principles that help think about this from Brian Arthur. One of them is a combination principle. Actually, technology consists of combinations of other technologies. And so here I sort of illustratively tried to trace from the invention of writing to the printing press to television to computers, and eventually give you that star-like thing is the internet. And you know, if you trace it backwards, each thing is chock full of technologies that have sort of come before. And a consequence of that is that there's more technologies as time goes by. So technology tends to combinatorically explode, exponentially explode. Then there's the recursion principle. And that says that technologies have parts that are technologies. So if we look at the graphical interface, that actually has parts for it. There's how you get stuff in, how you get stuff out, and so on. And then there's technologies for each part of these things. And if you broke those up, those would have technologies inside them as well. Until you finally get down to the phenomena principle, is that eventually, either indirectly, like because they refer to other technologies, or directly, because you're sort of bottomed out on it, technologies rely on some phenomenon or truism of nature. Now, the thing that took me a long time to understand is that that phenomenon can be sort of right on the surface, so you don't need science to do it. You just tinker around or just look at it. And with common sense, you can sort of find that out. That's sort of the case of the bicycle. Others sort of require science to do. So you probably wouldn't have figured out the phenomena of quantum tunneling by tinkering around. You probably actually needed science to do that. And then the working set and Fitts law and those sort of things are kind of higher up, but in the middle, maybe you would have got some of that by fiddling around. So technology is kind of the programming of nature, if you want to put it that way. You got to have some natural phenomenon. And science is what helps you sort of figure that out when necessary. Well, you think of every piece of technology. Can you really think of it as a phenomenon? What's the phenomenon of a truck? Well, a truck is a platform that's self-powered and moves easily. And it has, of course, a lot of phenomena in it. But one phenomenon is that gasoline yields energy when it's burned, and so that can move the truck. Another one is that the rolling friction is extremely low in things that have wheels, and so it moves more easily. So anyway, my second sort of thing that I want to note is that design principles are what put this phenomena together with a use for it. And so these are kind of the core sort of thing to pay attention to. And what theories with a purpose do is they just sort of set the stage for figuring these things out and using them. And they don't have to be human related, actually. They can be like the space of input devices that could be invented. That has a part that I guess relates to humans, but it also relates to all the mechanical innards of them. So there's one other thing that we have to get out of the way, and that's kind of how technology evolves in time, because there's a conclusion that comes from that. Well, it sort of does something that's like evolution, but that's another confusing thing because it also sort of doesn't. Brian Arthur refers to this as combinatoric evolution. It's not strictly like biological evolution, because biological evolution is blind hill climbing. So it depends on randomness and hitting the right things. Whereas technology evolution is created by people with intelligence to fill gaps. So it still evolves, because of part of the same reasons that biological evolution evolves, but you can actually step through the gaps by the limited amount of analysis you're able to do. And then, of course, it's standard engineering. It sort of learns and gradually progresses. This is part of what a lot of HCI practitioners actually do. They just want methods that sort of work, and there's always challenges in applying these methods. Radical engineering, though, depends on new principles. At CHI, we're sort of the guys who figure out the new principles, is how I think of it. Okay? And so, as this moves forward, there's a thing called the technological agenda. Technology is sort of a dual search through the space of needs on the one hand and the space of means or principles on the other hand. And you can actually start from either end. Sometimes, you know, you have a great widget and you find the use for it. But most technology arises in response to other technology because there's always, if it's a system, there's always a weakest part of the system. This is sometimes called the reverse salient. And so you fix that, and now that makes some other part of the system weak. And so there's a sort of cycle that Utterback and guys have found that technology goes through. There's sort of experiments just with using the technology. Then there's sort of a pioneering architecture that comes up and pioneering products. And finally, it settles on the dominant design. And after it settles on the dominant design, basically research and exploration stops. And you can't get stuff in there anymore. And then there's all these sort of settler projects that come out. So if you look at the history of the graphical user interface, you can kind of follow this through for the early days of experiments. And the yellow technologies at the bottom are where you kind of finally hit the element that's going to be in the dominant design. You can sort of watch these things sort of assemble themselves until finally you get a graphical interface Windows. And I think it's the Macintosh that really does the dominant design for this. It's the Alto that does the pioneering architecture for it. And then after that, as people at CHI complain all the time, everything seems to just be about Windows and keyboards and mice, and people want to get other things in, but they can't. Well, now if you look at that, we're clearly at the end of the dominant design of WIMP as a GUI. Try and use Windows to design these products. You know, that would, even Microsoft wouldn't try that. So, or would they? So there's only a few times when you can do things that are big, you know. And people, I've been on program committees at CHI where people are dismayed that nothing really great is happening now. And they think it's because the conference committee is lousy, the people in the field are lousy or something like this. It's actually partially reflecting the state of the technology in these great cycles. There's less than you can do about that than you might think. But now is the time of one of those times. But it doesn't last forever. So now I think we're back in the stages of the antecedent research and the pioneering designs. And one way that it's easy to see this is when you look around at things like the maker movement. I say things like the maker movement, and I use it as a sort of token for this, because there's lots of these that are going on right now. They're sort of harbingers of what's happening. So here's what's called a hack space, where people get together in a shared space and just work on the new technology and things that you can do with it. And there's arisen, I mean, this is just amazing to me. There's arisen this worldwide set of fairs around the maker movement where people come and exhibit stuff in their booth. This is a plotting of the major maker fairs in the world. Look at how many of them. Everywhere from Africa to to Silicon Valley. One of the, there's several instigators of this, but one of them is this notion that atoms are the new bit. So the fact that you can print designs. So here's a physical printer. You use, the great thing about this is that it puts the creation of physical objects into the digital world. So you design it in the digital world and then press a button and something makes it physical. And then, of course, you have the technology, the networking to create communities around these things. So here's a couple examples of devices that are making that work. The Arduinos allow you to package, build amazingly complex little devices, digital circuitry for them. 3D printers you can pay anywhere from $1,300 or maybe $1,000 and have one at home to here's one for $18,000. I was sitting next to somebody at dinner and I was remarking on this, and of course he pulled out of his pocket something he'd just printed on his 3D printer. Okay. This is only one of several sort of related movements that are like this. There's a quantitative self movement in which people measure themselves in various ways. So one of these devices here is one of my favorite. It's the, let's see if you can see it, maybe you can see it here. Can you see that? I can't see it. Well, it's the item up there on top. It's a scale, the withing scale. Withing stands for Wi-Fi things. And you step on the scale, and it takes your weight and takes your percent fat composition, sends it to your local area net, and on up into the internet. And something like 15 seconds after you've gotten off the scale, it's on your iPhone, all plotted in a plot for you. And the other device near it is a Zeo, and you wrap this around your head at night, and it tells you how many hours you spend and what type of sleep. And then you can figure out if I have coffee after 6 o'clock at night, do I not sleep as well, or stuff. There's life hacking, which is sort of how to use all this new technology, gizmos, to do time management and other things. And then one of my favorites is Instructables. In Instructables, somebody wants to tell you how to make something, so they break it down step by step with instructions. And then things like the Khan Academy. So in the Khan Academy, the idea is that there's lots of little, you took Algebra 1 or something, or Algebra 4, and you never did figure out how to do test for infinite series or something like this. There's little pieces of your education that are little kind of raggedy holes. You can get these little 15-minute videos that explain and fill in that hole specifically. So another reason why I like these is that they focus on education, and they focus on it in little units in a practical form. And so they allow you to do what you might call just-in-time education. And here's another take on the same movement. The Economist calls it the third industrial revolution, which is basically digital, things go digitally designed. So this is actually a big era that we're entering into. Institute for the Future calls it the era of the amplified individual. So individuals have great power. My favorite characterization of it is Hal Varian, though. It talks about it as a period of combinatoric innovation. You have the components, so the principle, based on these principles that we were talking before, you have components that embed those things and that are perfected enough so that they work. But the applications haven't yet been done for all of these things. So basically, with a small team of people, you can just take all of these components and make this and make that. And so on. And especially since more things have been put into the digital realm, it's really, we can really look forward to a lot of technology going fast. And when that happens, because this has happened before historically, then these inventions come into clusters and you get a technology boom. This is the internet boom. And of course there's the internet bust that comes after that, which is a typical part of the cycle. But the internet didn't go away. The really serious stuff of the internet kept going on. So anyway, my conclusion from this part of the examination is that we're sort of in a new golden age of HCI. But again, the period doesn't last forever, so there will be a new dominant design that emerges, possibly several in different areas out of this. But right now, we get to sort of do that. So back to HCI. So from the reflections, I get the idea that focusing on design principles is actually a good thing to do if you want to advance theory. And from the technology evolution, we're in the beginning of a new cycle. And from reflections on the maker movement, I like the fact that they cast the theory in terms of how to do stuff, and that they provide building blocks for stuff that's interesting to do in just-in-time learning. So I had an experience recently to be influenced by this idea. I made a couple lectures for a number of courses, but in particularly for Scott Clemmer's intro course. And other people have done this, and have used information or slides from me in the past, and I used slides from them. And after a while, by stirring the pot, you know, there was lots of contributions. If you looked at the slide deck that any one of us were using, we kept influencing each other. And I was particularly taken by Pat Hanrahan's, well, by first Bjorn Hartmann's version, which took apart a keyboard, and then Pat Hanrahan's version, which really got into how that worked to the point where the students could almost build one of these things. In fact, this was very popular in his class with the principals learned. So I did a couple lectures, my version, trying that, which start by disassembling the keyboard, and they get you through various levels, and finally you're into scan codes in the controller. And you end up with a layered model of input, seeing the different representations at the same layer. And then you go back and do this again for the mouse. And then you start generalizing to input devices in general. And then you start looking at new kinds of input devices and how this relates to that. But when you do that, then at the end of the class you say, but we've been talking about input device for an hour, and we haven't mentioned the user at all. Isn't there something wrong with that? So in the next class, the idea is to go through the same material again, but now from the user side, but in the same spirit. So calculating things that would be useful for the technology on the other side, so that to the extent possible, it's just sort of one seamless set of principles and mechanisms for computing things. So there's a computing of, you know, what are the arrangement of the keyboard, what difference it makes. There's another abstraction hierarchy for the humans. And when you work this out, in fact, you can see all of the parts of the course as visiting all of the pieces around here, and you kind of need theories all the way around that integrated with the other information you need to build stuff. So from that, what I liked about that is teaching the abstractions and theories from a maker point of view takes sort of the most abstract thing and the most practical thing and puts them together. So I'd like to sort of use that to sort of end with 3 applications of this idea or this attitude of doing things. The first is sort of a design methodology that we could get out of it, which you might call middle out design. With Scott Clemmer and friends and graduate students, with the medical school, we were working on a project to reduce medical errors by applying computer techniques to existing paper cognitive aids or checklists. And so you go in thinking, well, we just have to add the computation to this stuff. But of course, it's a much more subtle problem than you think. And the way I like thinking of it is that there's 2 sets of sort of principles that you're trying to do, from interviews, by watching simulations, by building stuff. One is, what's the core set of driving problems? This is not so obvious when you first start, as all of you who try doing similar things will know. And then what's a set of core design principles that you could use to solve them? And so you do a bunch of stuff, and this gets you to the middle. And then from the middle, you work out for the design. So here's just a gloss of some of the core driving task problems we found. And again, it's useful to lay them out by sort of abstraction layer. So there's things at the perceptual level, the cognitive level, the rational level, the social organization level, all working at the same time. Now, unless you sort of separate this, you can get awfully confused working on the problem. And for example, one sample core design principle that we're trying is that if we can use a common display for that shares information among people, we can reduce the amount of explicit coordination and then increase the amount of implicit coordination, and thereby allow the doctors to work with less error and more quickly. Now, there's issues that you then have to face with, oh, the screen gets piled up too much. Can you use another technique like degree of interest trees or something to manage the display and so on? So each problem, like we found in the case of the Windows problem before, the mission control problem, creates secondary problems. So usually for an invention, you have to come up with your key idea and then about 12 supporting ideas to make the key idea kind of work. The second application is what you might call education in the large. This is not what I mean by pie-shaped people. In the past, the idea was, well, we're going to educate students so that they're sort of T-shaped people. They have a lot of breadth, and then they have depth in one area. So if knowledge is a continent, you sort of know your way around at least part of that continent, and then you know this part that you're an expert in really well. But that kind of conflicts with the way the technology is going now, where there's many crossing pieces that like in the application that I was just talking about, you have to know something about medical errors, then you have to know something about statistics, then you have to know something about networking, then you have to know something, it goes on and on, all these little pieces. So this is one depiction of that island today, and this, of course, is just the crudest simplification of all the areas. And the way, in fact, people deal with this is usually they have their home discipline, and then they work in maybe some bringing that to some other area. So for this area, it suggests that actually, if we design people to be more pie-shaped, meaning there's not just one area of expertise, but there's at least one other, that might be a better educational frame, because a lot of work consists of taking results that are known in one area and transferring them over to another area. My third application of it is into what you might call education in the small. And the working title of this is Lambda Books. And the idea here is to do a new kind of book that uses computation to accelerate learning these principles in it. That increases the ease of communication with the textbook, has better representations and more detailed chains of causation. And the way of doing that is that the text is everywhere computational. Hence the name Lambda Books. It uses, there's a paper that I sort of like called Cognitive Design Principles. Barbara Tversky was part of this, and Pat Hanrahan and Minish, in which they went through a number of examples. One of them is designing a GPS system called Line Drive, which distorts the map so that the map has more of the information that you need for the trip and gives up a lot of stuff that you don't. And then another system for assembling things that figures out that you need step-by-step instructions, and you need this chain of instruction that goes from each of these. And the reason why animations don't work for this kind of task is that animations sort of don't stop you at the right places at the steps, and they overload your memory and so on. And so anyway, I think of this as another one in the series of trying to do things like that. And then it uses domain-specific languages. So there's an interaction language for the reader, which of course is simple but systematic. And there's a builder language for the author. And there's a lot of people trying to do electronic books and electronic textbooks right now, but this is what I sort of conceive of as its place in the firmament. The best way to learn something is with a human tutor, because a human tutor can keep resequencing the information with you, understands what you understand, and can keep optimizing the sequence from you. Maybe next best are intelligent tutoring programs, but these are very expensive to create. There's been some attempts to do better electronic textbooks like Al Gore's book and E.O. Wilson's book. But when I look at the credits for these, they have these huge 30-person teams and stuff. It's sort of like making a television show. And then there's a conventional text, which is still expensive and is static. So I imagine that you could get the cost down of creating one of these things so that even a mere professor could create one. You wouldn't need a special team. And yet you could get the effectiveness up. So I thought I'd give you a couple snapshots from how this might look. So imagine that we have a book on input devices. Okay, and one of the elements of the user language is going to be called these things called character actors. A character actor it's a character or a word or something that appears in the text and is treated just like a piece of text, but it can have action. So you can touch it with your fingers in various ways. That diagram is sort of summarizes the whole language. And you can build a lot of things out of these without, just from this simple language, you can sort of slide your finger along it or you can tap it, basically. And some of the words in the text would have some sort of indication on them, so you didn't have to press every word to guess if it could do something. So there's several ways of doing this. I've showed there one that has a kind of blurred shadow under the word, because you don't want it to be too distracting. Okay, so I'll show you a character actor application. And this one's trying to do three things. It's trying to do direct interaction from text to figure. See, one thing that would really be great is if we could get rid of the captions or get rid of a lot of the captions and go directly from the text, integrate it with the figure much more. And that's because a lot of energy is in figuring out what the correspondence of these is and looking back in forth. So you'd like to use more direct ways of doing it. So you'd like to use deictic reference. Instead of saying triangle ABC, the upper corner of it is whatever, it just shows you directly. And this also helps you with linguistic grounding. If you take Herb Clark's theory and all of the steps that have to be done in order to communicate to people or to machines, by having a computational substrate, we can do that, better job of that. And finally, it allows you physical and logical navigation of the technology in various ways. So here's a keyboard, and so here's some supposed text for it. And so we say, this is a PC-style keyboard. Whoops, what happened to my... Let's try again. Yes, there's a PC-style keyboard. And we press it again, it goes away. So we can point to things without having indirect symbolic means. We can start to dive into things and take them apart. We can extend this to where we use words or numbers or characters in a special kind of character actor called thermometer words. And so here, for example, is a piece of text that gives one of the computations. And as I slide this number back and forth, you can see the words, it does a calculation and puts all of the other things so that they work with, they're consistent. And just so that you can see easily what's happening, if the numbers go higher, they turn blue. If the numbers go lower, they turn red. And so instead of a calculation like we had to do before where we had upper bounds and lower bounds and so on, we can have sort of all the numbers in the middle of this sort of thing. And then finally, one of the parts of teaching people about these systems is representation shifts. So I was talking in that lecture about going from physical keystroke to switches to controllers to various things, and the representation of the input changes in form as you go through that. We can help people do representation registrations. So you can see the correspondence of two representations, what the same thing looks like in them, and you can follow this through. And so here's where you're touching one of the words, and it's making the figure operate. Okay. Well, okay, so that's my little essay. To advance theory in HCI, you have to understand how it works better than I used to with technology. And my conclusion is to concentrate on these principles, to realize that you don't always have to have science in it or theories. A lot of it can be intuitive. And to focus on practical use for this stuff. And in the examples I've showed you, I try to mix the device and human theory sort of all together. That's what the maker movement has sort of inspired in me. Okay, so that's.
Comments, questions? Please come up to the mic.
Hi, Stu. Scott Clemmer from Stanford.
Yeah.
I have a question for you about middle-out design. So, it's really fun to do research where you have a concrete user group, and you have the hope that if we try to solve these people's problem, along the way of trying to solve their practical problem, we'll have to invent new theories and come up with great new principles. And I think that often works. I definitely believe if you pull it, if you tug at a string from anywhere, you'll eventually get somewhere interesting. But the time scale is often longer than you can sometimes hope. And so I was interested, if your middle out story is a little bit different than the dual search story, where the dual search story is start at the two ends and find a place that ultimately connects them together. I've found that works really well, but it requires that you have a couple of different balls in the air at any point in time, and having enough but not too many is often difficult. I was wondering if you had thoughts on that.
Well, you have to distinguish between standard engineering and technology development. So what it seems to me you were talking about in the first case is sort of standard technology development, where somebody comes to you with a problem and you basically have a methodology for solving this problem, so you apply it. That's the state that we're trying to get to for most things done in HCI. I mean, this conference sort of distorts our view of this, because if you say, I use method 14 with company X, they don't let your paper in. But because it isn't new, they say. But almost all of what HCI is going to do in the real world isn't new, or it better not be. Because you need to build up a set of methods that can be used over and over again. So I agree that when you're trying to find new stuff or do hard stuff that you can't do that way, that it can be expensive. On the other hand, to analyze that mission control problem, that was a little bit novel, but that was really fast. It's an error to think that theory takes longer than experiment or observation, because if you have something concrete enough, it can be very much faster. That's why I want to integrate. This is sort of my insight, is if we could integrate it into the way people who take our courses just think about the problem, as opposed to it being the separate thing that you have to do. Notice that even in the first example I gave, even though there's an implication that that's a quantitative calculation, you don't have to do the quantitative calculation except for some special research project. All these quantitative things can be used qualitatively. Yeah, Ben?
Hi, Ben Schneiderman, University of Maryland. Thank you, Stu, for your talk and for all your work. Being at your talks always gets me to raise my game, which is a good thing. You focused on the technologies and the devices a lot, but I would say the excitement and interest now is about the social media, and the technologies are a different thing. We're not so much concerned about the physical devices, but the technology of how we coordinate, arrange social participation, motivate, etc. What's your thinking of what are the theory potentials for that space?
Well, that used to be the exciting new thing on the block. I think some of the physical stuff is come back, but I want to answer your question more directly. I don't see why you can't sort of do the same approach to that, especially like with your, there's some interesting theories in this area. Some of them involve net computations. You did one of the components that actually makes that possible. I could imagine integrating that in this kind of maker sort of framework, just like any other kind of technology. You think it's really different in kind?
I do.
I mean,
yeah.
I mean, it's true. I emphasize the gizmos and
Right.
stuff, and we don't have the peeling apart the physical stuff.
Right. It seems like these world of making devices and objects is one kind of thing, but the making of the mechanism of social participation, for example, has a different flavor to it. There's tinkering, okay, and there's building, and there's responding to user needs and so on, but it seems to me requires a different form of thinking, a different design space of possibilities.
Now, I bet I could do the same sort of thing
All right.
to that design space. He says brashly.
All right. We're waiting.
Because as you know from the series of meetings that you chaired and participated in, one of the claims was that, well, everybody gets on the social bandwagon and does stuff that's sort of doesn't have a prayer of working, that there's a way of doing it better and doing it
Right,
worse, for example.
The making of social, political, economic structures is different. The emergence of contributors, collaborators, and leaders are, a different phenomena than taking a few things together and putting them together and building something that's more optimal. There's something where the social process of independent entities emerging to have a social structure
Take the design of
potent.
aardvark. This is a system for social question answering. There's a fair amount of analysis that has to be done to make that work and understand how it works that I bet you could do with an approach like this. Like, you have to engineer people's willingness to answer questions to other people. You have to reduce the cost for it. You have to not bother them too much. You have to tune these social parameters so carefully.
Right, okay.
Now, if you're in an area where there's no theory at all, and it's completely empirical.
Okay, I think there's sort of emerging new families of theories or new kinds of theories, and I find that a pretty interesting, compelling opportunity. And I'm ready.
All right, I think I'm up next. Hi, Stu. Thanks for the thought-provoking ideas and reflection. One of the distinctions you made early on in the talk was the difference between science and tinkering, and I wonder if they really are different in kind. Maybe tinkering is just a kind of democratized science at a smaller scale.
No, I would say it's the thing you do to get into science. One of the things I like about the maker movement is people tinker and get to know the properties of these components. And in fact, in engineering, there was a movement years ago to put more analytical stuff into engineering. engineering. And that came at the expense of this sort of people knowing the materials and having this intuitive feel with them. I think both of them go together quite well. I mean, these pictures I showed you of the people in the hackerspace, they're all tinkering with those materials and trying this and trying that. If you can merge that with some principled analysis of what you can analyze, I think that's a magic combination. Do you disagree? Oh.
Hi, Stu. Michel Baudouin from Paris Sud and Stanford. As you know, we spent the last 2 years hanging out at Stanford, and apart from the academic life there, the two events that I will remember forever is the Maker Faire, which I'd never been to before, and the Bay to Breakers race. And for those who don't know, the Bay to Breakers is a race that goes from the Bay to the breakers of the Pacific Ocean in Stanford, in San Francisco. Some people run the thing for real, and a lot of people are there just to have fun and have these amazing costumes. And it was, for me, an amazing experience of, in a sense, social engineering, because people meet and talk and have fun together. And the link with the Maker Faire is that there is a social movement around the Maker Faire.
Right.
And I think it's inspiring because on the one hand you have all these people tinkering with things they don't always understand how they work, and at the same time you feel like some new things are going to come out of this. And if I make the parallel with the famous hackers computer club that is famous for being the start of the personal computer and the Apple one, among other things, there's a difference in scale. And so the question I have is, can revolutions come out of this large-scale movements where everybody becomes a tinkerer, as opposed to situations where you have a small group of people who have an interest as hackers to make their things available to others? In other words, is democratization necessarily an instrument for technological evolution or revolution?
Yeah, well, when you have these sort of revolutions in technology, they're often preceded by this kind of tinker period. Since you asked that question, here's examples of two of the previous ones. Now, not of the same scale as this, because you didn't have the social networking ability to put things together. So one of them is the late Sputnik, or late 50s Sputnik thing. And what's amazing is the Army made a model of rocketry that told you how to mix propellants and stuff. They would never do this now. And in one of those pictures is a picture of an electron diffraction machine that I made using hints in Scientific American. And, talk about the influence of this. I was once at Stanford, and a talk given by Don Herbert, Mr. Wizard. And afterwards, half of the auditorium went up to tell him that the reason why they were in science is because of him. And then the other side is the Homebrew Computer Club. And of course, there's the Altair, one of the first personal computers, and there's the Apple. And they kind of came out of that. And people, by talking and having this ferment with themselves, got ideas. Now, these don't last forever. These periods don't last forever. So this maker thing is, you can already see there's some people that are buying up the maker supplier companies and vertically integrating them and whatever. It's a phase. But when people get all these components, they don't know so much what to do about them, so they try this and they try that.
Thank you.
Jeff Johnson. I'm a big fan of both Ben Schneiderman and Stu Card, but in this case I'm going to side with Stu. So I went to a talk at UPA last year, and one of the speakers was a a VP at Facebook. And he said that he's asked all the time how to make something go viral. And he said that everyone's first impression of how you make something go viral is to get the information. If you look at a network of friends and friend connections, you see that certain people are kind of movers and shakers. That is, they have a lot of connections, both in links and out links. And the common wisdom is that you get the information to them, and whatever if enough of those people who are heavily connected become excited about whatever it is that you've sent them, the thing will go viral. But it turns out, according to this guy at Facebook, that's just wrong. So they did a network analysis of the friends connections, and what they found was that the thing that makes something go viral is not getting it to the highly connected nodes, but rather to get it to...
Let me guess.
Okay. Thank you, Mr. Simon.
The weak links.
Yeah, basically
Instead of the strong connections, the weak links.
It's the people who connect clusters, regardless of how many connections they have. So basically, if there's a large group of people who go to Chi and a large people who go to UPA, there might be one or two people who don't have many friends in both groups, but they don't have many connections overall, but they connect those two groups. That's who you need to get it to. And so basically, that kind of an analysis can work in that domain quite well.
Yeah, those people are called brokers.
Right.
And so you could compute that. You could take a database of people that are connected, and you could, with that amount of theory that you just said, I think you could compute interesting things relative to the social movement, probably using Ben's application that he and his students did for doing that.
Paul Resnick from Michigan. I want to make sure that I'm getting the right message. So I see the vision of there's components that people can recombine, and we get to a special time when we have democratization of who can use these components. I think you also have a message for what our role is, and I want to make sure I get that message. Is it that we're supposed to provide the components? We're supposed to notice what the things that the tinkerers are doing and come in with some design principles that can make sense of those experiments? What is it that we're supposed to do as Chi?
Well, first, yes, but secondly, you're supposed to provide the abstractions and the theory. I hate to use that as such an honorific word, because I mean something sort of practical. The abstractions and the means of thinking about that to do practical things with. So if people are thinking about all the ways these components will go together, a lot of them are a bad idea, probably. And you want to understand what's a good idea and what's a bad idea out of it. Like, there used to be all of these input devices now which look silly, but at one time nobody knew what was the way to do it. At one time people didn't understand as much about networks as we do now. So you're supposed to be providing the abstractions that allow people to do more than just guess about these things. And my suggestion is that we do that in a way that just integrates it in with the part that's fun.
Hi, I'm Richard Davis from Singapore Management University. I just was wondering if you could clarify something for me that I'm not sure I understood. You've been saying that this period doesn't last forever. I've been hearing you say that a lot. And I guess I'm not exactly sure what you're referring to. Are you referring to the maker movement itself, or are you referring to the opportunities to do something big?
Well, probably the maker movement in the same form. So the ones that are on the screen right now, those movements are gone now, although, you know, you can bring back elements of them. But right now you're in a situation where there's all these components that are available and nobody's really exploited them all in all the ways that can be available. So basically that's what people are doing. Now the principles that, you know, you teach things so that you can have some sort of practical focus with them. Maybe that stays.
Well, I guess the reason I'm asking is because I have the sense that there's always going to be another component, so won't there always be makers?
Well, what I was trying to convince you of is that these things come in cycles. So, you know, it's been 30 years that you've had to accept the Windows graphical interface the way it is. In fact, let me tell you about the dominant design and how it works. The dominant design is so dominant that people don't even think of designing alternatives to it for a while. So I once had the job of designing a new keyboard for Xerox's second version of the Xerox Star. And this keyboard had a calculator part of it. And it always annoyed me that it didn't go 1, 2, 3, 4, 5, 6. It went 7, 8, 9. And so I thought, I'm going to fix this. You know, I might as well, now's my chance. I can make the dreaded keyboard the way I jolly well want it. And then I began to think about that. And there's even, you know, there's more people who know the touch, who do have telephones than who have calculators. And there's even research results that says that that's the best way to do it. But then I started thinking of it. If I did it 1, 2, 3, if I did it 7, 8, 9, nobody would criticize the product because that's what was expected for every product. But if I did it 1, 2, 3, there was a small chance I was putting this major product at risk for a small gain. And rationally, it was not worthwhile to even take the chance of risking the product. So I went and did it 7, 8, 9. That's the dominant design, moving my hand in the design, so I couldn't do it the other way. Or look at the IBM keyboard. The IBM keyboard for the PC, I mean, people still use it. It has keys on it that have never been used in the last 20 years. There's some keys that there's an IBM PC keyboard for the Mac. There's some keys that have never done anything for the Mac. You know, why do they sell an IBM PC keyboard for the Mac with bogus keys? It's because of the dominant design. It's because people expect it to be that way.
No. Because I tried to get a key.
We're at the most enjoyable part where John
I was
gets
a vice president at Apple, okay? And I hated those keyboards. And I went and I told the keyboard people. And they said, look, this is what everybody makes. It's like $5. And if we wanted to change it, it would cost us money. And, you know, this doesn't really impact our sales. And so I failed.
Well,
everybody agreed with me, by the way. Nobody disagreed with the stupidity of the keyboard. It was just a matter of money.
Well, doesn't that sound like exactly the argument I'm making? It's the dominant design that it's going to cost you more, and it puts at risk, and nobody will come back at you.
It didn't put anybody at risk. That's the problem.
Well, I would have thought that some people would ask Apple for a keyboard that's standard.
All right.
Thank you very much, Stu, for a great talk. What?
Take 2 more.
Yes, exactly. My name is Anna Mary. I'm from Virginia Tech, and I love this talk. I'm active in the maker community, and of course among you all as well. So in reflecting on how we do things in academia and in maker community. I see a couple of there's definitely similarities. So in the maker community, people talk a lot about the step-by-step, the tinkering, the failures, right? Through forums, through online, through the mediums of Instructables, talking a lot about step-by-step detailed instructions on how to make these things. Whereas on the side of kind of academia, I see that we definitely do the reporting through our papers, publications, these conferences. But it's not as much about the tinkering. We don't report as much about the failures, the little details that make or break our systems, our designs, sort of thing, not as much as the sort of the spirit of the maker community. So what I'd like to ask is, if we're in a golden age of Chi, how will we change? How will this HCI community change in the influenced by the maker community, and vice versa as well?
Well, for one thing, you're not going to see so many papers about keyboards, mice, and CRTs. There's just, for a while, everything had the same interface, and that's not going to be true again. And there's this big search that's going off for example, the iPhone has an interface that you can do input with it, but it's not great. You know, somebody's going to come up with the definitive solution to that. So where I see the similarities is that maybe it will start from something that somebody tinkered with to start, and then be developed. But yeah, I guess that's my answer on that. I like the energy of the maker community and the energy in the students. And I like the step-by-step instructions because you can do it.
Exactly.
Now, partly that's to compensate for knowledge on the person receiving the instructions.
Stu, thanks a lot. Great talk.
They want a reprieve for.
Stu, thank you for inspiring the field and continue to do so after decades of your work. Just one point to support the dominant design paradigm. I actually know one reason the IBM keyboard still had the keys people don't use. Even at the time when I joined IBM in the mid-90s, we still used actually VM business software, which required F12 to print something. Without that, you wouldn't be able to do. So it just shows the dominance and the backward compatibility and interconnections.
Why did you
have done?
Why did you have sysrec?
I'm sure there's some software used that, but I want to ask you is some of the components theories that I found very useful comes from classic psychology, such as perception, cognition, motor control research, and you and others put these together and make them more like engineering models, so you can actually compute. Can predict designs. I wonder, the more modern psychology today, which are mostly neuroscience-driven, as I perceive it, whether they're providing new insights that we can use for higher level, more engineering-like models, in your view?
Yeah, well, that's actually an interesting case, because the problem with psychology before was it was essentially a black box science. You had inputs and outputs, and you had this awful identification problem of how stuff worked in the middle. Now that you can get inside the box, you have a lot more constraints on what could be true. Now, it turned out, I'm not sure I would have predicted this, it turned out that all the classical psychology experiments set up essentially establish paradigms for the neurosciences to try and see if they could find a neuroscience explanation of. So for a while at least, a lot of the information went from psychology into neuroscience because the psychologists had identified and characterized these different phenomena. But now you're starting to get sort of stuff coming out. And I think neuroscience is a way of sort of grounding the black box and making things interesting. So I think it's going to be fantastic. So if you take the ACT-R theory, which started out as an information processing theory, it tried to put psychological data and replicate it with a general universal model. Now that's been recited so that it connects directly with neuroscience data. And then they fight about whether it really does or doesn't and whatever, but that's sort of what's happening. And there's a number of models that are kind of coming across this boundary. Eventually that'll help establish phenomena that come back into HCI, like the characterization of human behavior in terms of system 1, system 2. System 1 being an automatic system, system 2 being a rational system. Trying to put together how that complicated attentional and effort mechanism works has been really hard, and it looks like you're really making some explanation or some progress on that. That then helps conceptualize problems in HCI, like the problem of driving, or even in the example I was giving you of the medical application, the problem there is that it's a paced task, and the displays you make for people are not what they're supposed to be looking at. So they're peripheral. You're trying to get important information in peripheral displays without cognitively adding load to these people. That's an interesting thing to try and have to do.